around the Lagrangian, the symplectic manifold is symplectomorphic with P star L with its canonical symplectic form. And so, as a consequence, if you want to study deformations of the Lagrangian submanifold, you can just look at what happens in the local model in P star L and say that we look at C1 small deformations. That means that we look at sections of T star L for which the image is Lagrangian here. And again, it's well known that if you take such a section, alpha, which is a one form on L, that its graph is Lagrangian exactly when the one form is closed. And moreover, if you have two closed one forms, alpha and beta, so that their graphs are Lagrangian, and these two Lagrangian submanifolds are related by a Hamiltonian diffeomorphism, exactly when their cohomology classes are the same. So the conclusion is that the moduli space of Lagrangian submanifolds under the equivalence relation by Hamiltonian diffeomorphisms can be identified with H1 of the Lagrangian. And so, yeah, so this is a very nice moduli space. In particular, it's finite dimensional for compact Lagrangians. And so this is the starting point. Now we can wonder, well, log-symplectic manifolds are a kind of Poisson manifolds which are very similar to symplectic ones. So we can wonder how much of this story still goes through in the log-symplectic case. And this is the question that I'll try to address in this talk. So the first thing is, well, so as log-symplectic manifolds are Poisson manifolds. So first I will say what we mean by a Lagrangian submanifold in a Poisson manifold. So, well, Lagrangian submanifolds seem to be much less common than coisotropic submanifolds, but still there are some definitions that appear in the literature. I will use the one that appears in the book by Weismann, and we call a submanifold L in a Poisson manifold Lagrangian if for each point of L the intersection of TPL with the tangent space to the symplectic leaf is a Lagrangian subspace of the symplectic vector space, tangent space to the leaf with the symplectic form at that point. So yeah, so if the Poisson manifold is actually symplectic, then this reduces to the usual definition in symplectic geometry. And maybe another interesting case would be when the Lagrangian has clear intersection with all the leaves, because when the submanifold has clear intersection with all leaves, because then it's Lagrangian exactly when the intersection with each leaf is Lagrangian in the sense of symplectic geometry. So let's look at a few examples. For instance, let's take the linear Poisson structure on SO3 star. So its symplectic variation is by concentric spheres centered at the origin. And a plane here is Lagrangian exactly when it passes through the origin. Because planes through the origin, they intersect the spheres in something one-dimensional, so it's automatically Lagrangian. And well, if the plane doesn't pass through the origin, then it's tangent to one of the spheres. And at this point of tangency, well, this subspace is all of the tangent space to the leaf, so it's not Lagrangian. And the second example is well, is something similar to an example in symplectic geometry. So in symplectic geometry, we know that the graph of a symplectomorphism is always Lagrangian in the product. And in the Poisson case, we have something similar, but we have the graphs of Poisson emergence are Lagrangian in the product. Okay, so So let's move on to log-symplectic manifolds. So a Poisson manifold is called log-symplectic. Well, the manifold has to be even dimensional, dimension 2n, and the Poisson tensor is log-symplectic if wedge n of pi, which is a section of the line bundle wedge to n of tm, and this section has to be transversed to the zero section. So this is clearly a relaxation of the condition being symplectic. So I will always denote by z the singular locus, which is the set of points where wedge n of pi vanishes. And so away from the singular locus, the Poisson tensor is symplectic. And along the singular locus, it drops rank. And because of this transversality requirement, the singular locus is a smooth hypersurface. And it's in fact a Poisson submanifold. So it has an induced Poisson structure, which has corank 1. And this corank 1 Poisson structure is a bit special because it has a Poisson vector field transverse to the symplectic leaves. And this vector field is obtained by taking a modular vector field on M and restricting it to singular locus. So modular vector fields have tangent to Z, and they are also transverse to the leaves. So as an example, let's look at R2n with the standard coordinates. And this Poisson bivector is log-symplectic. The singular locus is given by y1 equal to 0. Oh, sorry, y1 equal to 0. And it has an induced corank 1 Poisson structure for which the leaves are level sets of the x1 coordinate. And the modular vector field in this case, well, with respect to the standard volume form, is del x1, the vector field here. And as a consequence of the Weinstein splitting theorem, actually any log-symplectic manifold looks like this around a point in the singular locus. So this is the local model for any log-symplectic manifold around a point in the singular locus. Now, we want to look at Lagrangian submanifolds in log-symplectic manifolds. And we want to look at their deformations. And so the behavior will depend on how the Lagrangian intersects this singular locus. So the simplest case would be to ask that the Lagrangian is transverse with Z. And this case is already treated in the thesis of Charlotte Kirchhoff-Lukat. And this case is the easiest case because you can use B-symplectic geometry in this case, which basically reduces it to symplectic geometry. So this formalism of B geometry deals with well, B manifolds, which are pairs of a manifold with a specified hypersurface. And so, well, log-symplectic manifolds are such examples. But also the Lagrangian, which is transverse to Z, is such an example because it inherits a hypersurface, just the intersection of L with Z. And so that's why in this case, this B-symplectic geometry formalism can be used. And so it's well known that a log-symplectic structure pi can be inverted to a kind of singular symplectic form, a B-symplectic form, which I call omega here. And in this case, we have a Lagrangian neighborhood theorem similar to the one in symplectic geometry. Around a Lagrangian transverse to Z, the B-symplectic manifold M omega is equivalent to the B cotangent bundle of L. And as a consequence of this normal form, the moduli space of Lagrangian deformations by Hamiltonian diffeomorphisms is now the first B cohomology of L. And this can be expressed in terms of usual Drama cohomology, like this. And so again, as in the symplectic case, you get a finite dimensional moduli space for at least for compact Lagrangians. And I will look at the other extreme. So I will look at Lagrangians which are contained in the singular locus. And it turns out that there are two possibilities for such Lagrangians. So if the manifold M has dimension 2n, then either the dimension of L is n minus 1, in which case its connected components lie inside leaves. But so for our purposes to deform such Lagrangian in the log-symplectic manifold, I guess this is less interesting because, well, outside of the singular locus, the manifold is symplectic, and there a Lagrangian would need to have dimension n. So this Lagrangian can never escape from the singular locus. So if you look at deformation theory, you wouldn't even notice that we are dealing with a log-symplectic manifold. It would just be deforming L in a very nice corank-1 Poisson manifold, which can maybe also be interesting, but I didn't look at that. I only look at the second case, which is the case where L has dimension n, so it's of half dimension of the ambient manifold. And in this case, L is transfers to the leaves of C. So L inherits a foliation from the singular locus. So this is the setup that we consider. We focus on half-dimensional Lagrangians in the singular locus. And also for simplicity, I will only look at Lagrangians which are compact and connected. And this assumption is not always necessary, but I will mention where it becomes important. Okay, so if you want to look at deformations of the submanifold, it's useful to have a normal form around it. And we will construct such a normal form in two steps. So we first make a normal form for the singular locus around L, and then we use a normal form for the log-symplectic manifold around the singular locus, which is already which is well known and which has appeared already. So, but the first step, this actually holds in more generality. Say that you have a Lagrangian in any Poisson manifold, which is transversed to the leaves. Then, well, the requirement that L is Lagrangian and transfers to the leaves, this fixes the dimension of the leaves that L can meet, just by the usual formula in linear algebra that relates the dimension of a sum and intersection of subspaces. So a Lagrangian transfers to the leaves can only meet leaves of a certain dimension. And as a consequence, the Poisson tensor is actually regular on the neighborhood of the Lagrangian. And since L is transversed to the leaves, so it inherits a regular foliation, which we call FL. And the local model for the Poisson structure around L lives on the cotangent bundle of this foliation, T star FL. This cotangent bundle has a canonical Poisson structure. It's just defined by taking the symplectic structure on T star L and pushing it forward along the restriction map, which takes covectors on L and restricts them to the leaves. So this gives a canonical Poisson structure on T star FL. And its decomposition in symplectic leaves is as follows. So its foliation is the pullback foliation of the foliation on L. And every leaf is just the cotangent bundle of each leaf of L with the canonical symplectic form from cotangent bundles. And so this is indeed the local model around the Lagrangian. The Poisson manifold is diffeomorphic with this one. So this is really like a foliated analog of the Weinstein-Lagrangian neighborhood theorem in symplectic geometry. And you can also prove it really in a completely similar way, just by applying the argument from symplectic geometry smoothly along the leaves, which is possible because the foliation is regular. But I guess it can also be obtained in many other ways, for instance, with Dirac geometry, or or even 2 weeks ago, I heard that Aldo is also working on normal forms around Lagrangian submanifolds. So maybe also using these methods, this can be obtained, or at least a local model. I don't know. So
yeah, you can, but
you can. Okay.
Yeah.
Good. So we want to apply this first step, of course, to a Lagrangian in the singular locus. So it says that the singular locus around L looks like D star FL with this canonical Poisson structure. Now in step 2, we just use the normal form around the singular locus, which is well known and which appears in work of Guillemin, Miranda, Pires, and says that the local model around the singular locus is its normal bundle Z times R with this log-symplectic structure. So it involves the Poisson structure induced on Z, the Euler vector field, and it involves the choice of modular vector fields on M, and you take its restriction to Z. So there is a bit of freedom in this formula. You are free to choose any representative of the modular class, and this will be useful in the following. So now if we combine the 2 steps, so say we start from here on Z times R, we have this local model, and we know from step 1 that we can replace Z by D star FL by using a Poisson diffeomorphism, which takes pi on Z to the canonical one on D star FL. We just extend it by the identity on the second factor, so it takes T del T to itself. And this Poisson diffeomorphism, it takes this modular vector field to wherever it takes it. Let's call it V for now. So the log-symplectic structure around L looks like D star FL times R with this thing, which is by now not very satisfactory, because normal form should only involve data that is canonical or that comes from the Lagrangian L, and this V has little to do with L. So that's it's not very good for now, but we can use the fact that in step 2 here we are free to choose any representative of the Poisson cohomology class of V mod on Z. So that means that also here we can choose any representative of the Poisson cohomology class of V. And to do that, let's look at what the first Poisson cohomology is of D star FL. What is this cohomology where V lives? So this holds in generality, say that if you have any foliated manifolds L, and we denote as follows the space of projectable vector fields. So these are vector fields whose flow preserves the foliation. And these vector fields have the property that they can be lifted to D star FL. Because for such a vector field on L, you can take the cotangent lift, which lives on T star L. And actually, the push forward under the restriction map is well defined. So this gives a vector field on D star FL, and it's automatically Poisson just by the way this canonical Poisson structure is defined. So these projectable vector fields, they lift to the cotangent bundle. And this is used in the computation of the first Poisson cohomology. So if we take D star FL with its canonical Poisson structure, then the first Poisson cohomology has 2 components. It's the first foliated cohomology of FL, and then the quotient of projectable vector fields by sections of the foliation. So that the first factor is the same thing as H0 of the foliation with values in the normal bundle. And so the isomorphism works as follows. If you take a closed foliated one form gamma, and you can pull it back to total space and apply pi sharp, then you get a Poisson vector field. And this vector field is actually vertical and fiberwise constant. And if you take a projectable vector field X, then, as I said before, it lifts to a Poisson vector field on P star FL. And so this thing computes the first Poisson cohomology. And so we can apply this to this V here. So for V, we can take any representative of its cohomology class. So the class of V corresponds to a class of X and a class of gamma here. And we just choose representatives, X and gamma. And this gives the following normal form. So the log-symplectic structure around the Lagrangian L is T star FL times R with this log-symplectic structure. So the canonical one on T star FL, the other vector field, and here, as I said, well, a representative of the class of V under this isomorphism. And so this looks better as normal form because now we use data from L itself. We use this vector field X and this one from gamma. And so I will use X and gamma for the rest of the talk. So let's try to remember X and gamma is the fixed data that come from the modular vector field. Okay, so now if we want to look at Lagrangian deformations of L, we can just look at what happens in this local model that we just found. And we just look at sections for which the image is Lagrangian. And so such a section of T star FL times R, it has two components, a foliated one form on L, and a section of the trivial line bundle, so a function on L. And well, in the local model, T star FL is the singular locus. So the first component should be thought of as deformations inside the singular locus. And the function tells you whether or not you're moving outside of the singular locus. So when f is 0, you stay inside the singular locus. If not, then you really move out of it. And now we can just compute directly when a section here is Lagrangian. And this gives the following two equations. So alpha has to be foliated closed, and f has to satisfy this equation, where, as we see, the gamma and x appear. So this data coming from the modular vector field. And so here is the first difference with the symplectic case. So in symplectic geometry, the Lagrangians are given by a linear equation, just d alpha is 0. So this equation is not linear because there is this term f times Lx alpha. So it's a little bit more complicated. Yeah, but still, it's not too bad, I guess. Another observation is, if you only want to look at deformations that stay inside the singular locus, then you set f equal to 0, and then you're just dealing with the closed foliated one forms. So it's very analogous to the symplectic case. So let's look a bit more closely to the second equation here. So we know that gamma is closed, and because of the first equation, also alpha is closed. So this here is a closed one form, and it's a general fact that if you have a closed foliated one form, then you can use it to define a new differential, which is the foliated differential plus wedging with this one form. And because eta is closed, this is the differential. And let's note the cohomology like this. So then we can rewrite the second equation as f needs to be closed with respect to the foliated differential twisted by gamma minus Lx alpha. So Lagrangian sections are given by these equations, which are the two closeness conditions. And so we also see here that although the equations are not linear, you can solve them in 2 steps, and each step is linear actually. So you solve the first equation for alpha, which is a linear equation, and then for fixed alpha, the second equation is linear in F. So so that the problem really breaks down into 2 linear problems. And so geometrically, these 2 steps, they amount to the following. So if you would deform the Lagrangian into the graph of alpha f, then, so I said the first step is solving for alpha, which is a closed foliated one form. And the first component represents deformations inside the singular locus. So the first step is you deform the Lagrangian into the graph of alpha, which is a new Lagrangian in the singular locus. And then the second step is you solve the second equation for f. So you find f lying in this cohomology group. And the second step represents pushing the graph of alpha outside of the singular locus. So the deformation problem can be done in these 2 steps, where each step is linear. Okay. Now there is this general principle that for every deformation problem there should be a DGLA or an infinity algebra associated to it. And also in this case, this is true. So the equations that we just found for Lagrangian sections, they are actually the Barrett-Cartan equation of a differential graded Lie algebra. And yeah, so the DGLA is described here. It lives on sections of exterior powers of the local model. These are F times R. And in a certain degree, such a section consists of 2 components. It's a foliated form of a certain degree, and a foliated form of 1 degree less. And well, these are the structure maps, so a differential and a graded D bracket. So the formulas are not very important, just the differential consists of 2 components, the foliated differential and the foliated differential twisted by this gamma. And the bracket involves taking Lie derivatives along this x that comes from the modular vector field. And so the fact that this DGLA governs the deformation problem, it means that well, the solutions of its Barrett-Cartan equation are exactly the Lagrangian sections. And so this is the Barrett-Cartan equation. And yeah, if you would write down this equation, then you see that we recover exactly the equations here that we already found. So this is the DGLA that governs the deformation problem. And yeah, so whereas in the symplectic case, the underlying algebraic structure was just a cochain complex. Or if you want a DGLA with 0 bracket. Now we have a DGLA with non-zero bracket, but still the bracket is quite simple. It only has a component in the second factor, taking some Lie derivatives. Okay, so in the last few minutes, how much time do I have left?
How much do you still need?
I don't know, 5 or 10 minutes. But
That's fine. Don't worry. Yeah.
Okay. Okay. So now I will talk about some geometric properties of the deformation problem. So one question we can address is it always possible to push the Lagrangian out of the singular locus? Or maybe are there some situations when small deformations have to stay inside it? And the second question is the deformation problem obstructed? So this gives an indication about smoothness of the space of deformations. Yeah, and so in the paper with Marco, we also have some some statements about moduli spaces. So you can also you can introduce equivalence relations on the space of Lagrangian deformations by Hamiltonian isotopies or by Poisson isotopies, and can discuss the moduli spaces and maybe find some situations when the Lagrangian is rigid, so that all deformations are obtained by applying such isotopies. But so I will not talk about this now. So let's address the first two questions. And to do that, this is why I made the assumption that the Lagrangian is compact and connected, because then this has some implications for the foliation that it has. So there is this general fact that if you have a manifold that is compact and connected, and it has a codimension 1 foliation defined by a closed one form, then there are two possibilities for the foliation. Either it's given by a fiber bundle over S1, or all leaves are dense. And so this statement applies to our case, because we are looking at Lagrangians inside a singular locus. So they have a codimension 1 foliation, and it's defined by a closed one form, because the foliation of the singular locus is defined by a closed one form. So you just pull that one back to L, and you have a closed defining one form. Okay, so in the following, I will always consider these two cases separately. Either you have a vibration, or the leaves are all dense. Okay, so first, let's look at when are deformations, when do they stay inside the singular locus? So if we look at the picture here, so I said alpha means deforming inside the singular locus, and F means going outside it. And this F has to belong to this cohomology group. So asking that small deformations stay inside the singular locus means that we should ask this cohomology group is 0 for small alpha. So we require that this H0 twisted by gamma minus Lx alpha has to be 0 for small alpha. That would mean that small deformations stay inside the singular locus. So yeah, so to solve this question, we would have to look at what is this H0 twisted by a closed one form. So let's compute it in our case. So if eta is any leafwise closed one form, then let's first look at the case where the foliation is a vibration. Then there is a vector bundle, which I denote by curly H1. It's a vector bundle over S1, and the fiber over a point Q is H1 of that leaf, H1 of that fiber of the vibration. And the first foliated cohomology is isomorphic with sections of this vector bundle. So now if eta is closed, then it defines a class in H1, or so correspondingly a section of this vector bundle H1. And it turns out that this H0 twisted by eta is isomorphic with the space of functions on the base S1, for which the product with this section defined by eta is 0. So this is the annihilator ideal of the section defined by the class of eta. And in the second case, if you have dense leaves, then it's much simpler. This H0 is either one-dimensional if eta is exact, or 0 if it's not exact. So now let's look at when can we push the Lagrangian out of a singular locus, and when is this not possible? So first, it is a situation where you can always push it out. It's if gamma is exact. So this means that Well, so gamma was like the vertical component of the modular class. So this means that there is a modular vector field tangent to the Lagrangian. And then there is always a path of Lagrangians not contained in a singular locus. And at the opposite extreme, so let's first look at the vibration case. So we would want that this group is 0 for small alpha. So in particular for alpha equal to 0, we should start with gamma. Well, the section defined by its class is nowhere 0, so that this is actually 0. So we start with gamma, nowhere exact on none of the leaves. And we wonder, then is it true that also gamma minus Lx alpha is not exact on all the leaves for small enough alpha? And that's true because the map which assigns to the closed one form its section in H1 is continuous for C0 topology. So for C0 small perturbations, this section of gamma is still nowhere 0. And we take here one derivative, so we should restrict to C1 small deformations. So this gives this proposition: if in the case of vibration, if the gamma that we start with is not exact on all the leaves, then C1 small deformations of the Lagrangian stay inside the singular locus. And in the dense case, it seems to be more difficult. So let's ask the same question. We want that this is 0 for small enough alpha, in particular for alpha equal to 0. So we start with gamma that is not exact. And we wonder, is gamma minus Lx alpha still not exact for small enough alpha? But this is not the case in general, but it is true when H1 is finite dimensional. But even in that case, the conclusion is a bit weaker. If we have dense leaves and H1 is finite dimensional, then if gamma is not exact, there is a neighborhood of the Lagrangian in C infinity topology only, for such that deformations inside this neighborhood stay inside the singular locus. So yeah, since this C infinity topology is generated by this increasing sequence of CK norms, you could rephrase it as there exists some K such that CK small deformations stay inside the singular locus. So yeah, I don't know what K is. And my guess is also that this is not optimal, that this can be improved to C1, I think. So here's an example where, well, the formula doesn't really matter, but just the Lagrangian is T2, and its induced foliation is a vibration. And in this case, gamma is d theta 2, which is not exact on the fibers. The fibers are copies of S1. And so we are in the situation of the first part of the proposition. So small deformations stay inside the singular locus. And the second example is meant to illustrate that it's necessary that H1 is finite dimensional. Well, so again, the formula is not really important. It's just we make sure that the Lagrangian is the 2 torus, and that its induced foliation is the Kronecker foliation by slope lambda. And so the Kronecker foliation has this somewhat strange property that its Fourier cohomology depends on which kind of irrational number you consider. So it's one-dimensional for generic irrational numbers, but for Liouville numbers, H1 is infinite dimensional. And so to get a non-example, let's take a Liouville number. And in this case, you can construct on the torus a one-form gamma that is close but not exact, but that has very small perturbations that are exact. And these allow you to construct arbitrarily small Lagrangians, which are not anymore contained in the singular locus. Yeah, so I guess I don't really have time for obstructedness. I will just say in 1 minute maybe. So obstructedness is about extending first order deformations. So if you have a DGLA and you have a path of Morel-Cartan elements, so a path of deformations, and you differentiate at time 0, then you get a solution of the linearized Morel-Cartan equation, so you get a closed element in degree 1. And obstructedness is about the converse. So it asks, is any closed element in degree 1 tangent to a curve of deformations? And when that is the case, this tells in a way that the space of deformations is smooth because the velocity vectors to paths of deformations, they form a vector space. So this plays the role of tangent space. And obstructedness can be detected by the Kuranishi map, which is defined for any DGLA or infinity algebra, and it's just taking the binary bracket in cohomology. So if you have an unobstructed deformation, then its Kuranishi map is 0. And well, so in this case, you can write down examples for which the Kuranishi map is not 0. So our deformation problem is obstructed. Let's not go into that. But so this is in contrast with the symplectic case, because in symplectic geometry it's unobstructed, and in our case it's obstructed. But what I want to say is that even though the problem is obstructed, there are computable criteria for unobstructedness. So you can tell exactly when a first order deformation is obstructed and when it's not. And most remarkably is that here that 1 and 2 are equivalent. So alpha f, the first order deformation, is smoothly unobstructed exactly when the Kuranishi map vanishes. And this is quite special because the Kuranishi map is a very weak obstruction. It only tells you when you can extend the first order deformation. Well, if you want to extend a first order deformation to a formal path of solutions, then the Kuranishi map being 0 tells you that you can construct the second term in this power series. So this is a very, very weak obstruction. If it vanishes, you can only find the first 2 terms in a formal power series extension of the first order deformation. But since the problem is so close to being linear, this is actually enough to find a smooth path of deformations that extends the first order deformation. And so the last 2 are also some equivalent conditions. The third one seems to be quite computable. It's just asking that the Lie derivative is exact. And the fourth one is maybe a bit surprising because it doesn't depend on these data X or gamma that come from the modular vector field. It's just asking that closed fully that one form extends to a closed one form. Okay, so sorry for going over time. I will stop here.